You guys should know by now. Tonight we have a guest, Morgan Bailey, NJ8M. And Morgan is going to speak to us about one of his ham radio passions, which is antennas. And first, just a little bit about Morgan. He's been a ham for a long time. First licensed in 1967. That's over 50 years. That's pretty good. And sounds like one of your first stations, Morgan, was an ARC-5 transmitter and a BC454 receiver with a power supply made from a TV transformer and tubes. It actually sounds like what I started off with. And Morgan was interested in CW and got into the traffic handling, got into contesting, and has spent a lot of time over the years traveling, as he mentioned earlier, and has built many different types of antennas in many different locations, and also has Elmered many hams. And in fact, is currently I'm not sure what you call it, if it's a mentor or an advisor with the CW Ops program, where you can get some assistance in improving your CW. So very good. And Morgan is going to talk to us tonight about end-fed wire antennas. So why don't we turn it over to you, Morgan. And you can start screen sharing. You will need to unmute yourself, Morgan.
Well, all right. I'm a fairly opinionated person about antennas, and I think the best antennas you can make are the best antennas you can get are the ones you make. I'm going to screen share now. Where am I screen share at? End-fed antennas have hit the market really big and hard. There's a lot of history of them, but there's a lot of confusion about them, what they are, what they aren't, what they can do, what they can't do. About antennas. Oh, I've got the greatest antenna in the world. Everybody says I got the greatest antenna. Well, if it's the only antenna you ever had, it is the greatest antenna you ever had. If it costs a lot, it must be good. That's pretty much totally garbage. Any antenna that is small and has an SWR of 1:1 is great. Really? Not so much. I've worked all over the world on my dummy load antenna. True, you can do that. QRP does work and it works well, particularly with 280 sunspots, which we haven't seen for about 15 or 20 years. So anyway, you have to put everything in perspective. In other words, it's relative. Antenna basics. You don't get something for nothing. The general formula for getting anything to be resonant is 468 divided by frequency in megahertz leaves length in feet for a half wave. That goes back to your basic test that you have to take to get your first license. They're either excellent, efficient, large versus poor, small, and lossy. More money does not buy a better antenna. And the thing that just hit the market is the go-to antenna. It is a $500. Yes, that's what it is. Best antennas are the ones you understand and make yourself. And one thing you have to carry in mind when you're designing or building or any kind of antenna is that 3% of the band frequency is 2:1 SWR bandwidth. And that's as good as it gets. If it gets more than that, then there's loss in the system. What does this actually mean? Well, let's see. 3% of 3.5 megahertz is 105 kilohertz. That's about all you're going to get on an 80-meter antenna under SWR at 2:1. On 40, oh my goodness, well, it's 210. So you just about get the whole band. On 20, well, that's another story altogether. You get the whole band on 2015-10. So you're good to go. That's why beams work pretty good for the whole band most of the time if they're full size. Complexity, radio complexity today is such that, most people don't even own a heat capability hot air soldering equipment to put surface mount chips on a board with, much less any way to etch a board in the beginning. So a ham radio used to be about building their own equipment. Unfortunately, with the cost of test gear and the component shortage needed to fabricate radios, cost is fairly prohibitive. Commercial radios are the way to go for the best solution. They'll get you on the air and they're reliable and they're clean. And good to great antennas are simple and they are relatively cheap to build. The end-fed half-wave evolution. First off, everybody learned what a half-wave antenna was. Well, I want more bandwidth, so I made a folded dipole. And then it evolved into C, which is a half wave linked with a quarter wave matching section. That's your in-fed half wave. And it goes by a lot of other names that date clear back to World War I/II area, and an in-fed ZEP, as in Zeppelin. What they did is they strung out a 135-foot piece of wire behind the Zeppelin, and they used a piece of ladder line that was a quarter wave length at the frequency they were operating, and they reeled the line in and out to get the best match for the power amplifier. The Zeppelin are first in-fed half antenna, so there you have it. That's what it looks like. But what else does this look like that many of us use today? 2-meter J-pole. 2-meter J-pole is nothing more than a half-wave antenna with a quarter-wave matching system, and then you slide your match up and down the quarter-wave and half-wave to get the one-to-one or the frequency where you want to operate. So, in-fed half-wave matching. An in-fed half-wave is, the impedance is about 2,500 ohms, 2450. This circuit right here is equivalent to a quarter-wave matching stub. It's only usable on one frequency because none of the values in this schematic are variable. So it's only good for one frequency. One would have to have one of these tuned, parallel link fed networks tuned to each frequency that you wanted to operate, 80, 40, 20, 15, and 10. So you'd have to have different antennas and really a pain. So a lot of people fell out of vogue with a lot of people. So the in-fed, I want this antenna, I want it feed it close to my house. So they made a parallel network circuit, which you can see, it's a parallel matching, but it's tappable. Get over here, mouse. It's tappable here for this to give you a ratio. Then it's tunable here for best. And then it link matches, 50, 75, 100, 200 ohms with another link, and it's an open link couple. And so it worked pretty good. And it was a nice antenna. Some people even right here at the bottom put a ground down to an earth ground, and that has some effect. We can talk about that later, but I didn't find it really much to talk about per se. Now, what did we do? We had that, and that was very complex. It was a very complex antenna in that area. Because every time you change frequency, you had to get up off your butt and go out and retune the darn thing. And the antenna itself was radiating RF close. If you wanted to get the tuning solution close to your shack, you had to tune it inside the shack, and there was RF problems. But we didn't know any of these RF problems. We didn't care about them because back in the area when these were really popular, no one had any computers in their shack. They all had tubes, and that was about the size of it. So enter the toroid. The toroid inductor revolutionized a lot of things in ham radio. And the biggest thing that toroids did was make everything smaller. They came into existence by Amadon in 1960s. And first they were only iron powder core. They mixed a bunch of iron with some sticking agent. Then they put them in a huge press and pressed them down, compressed them. Then they baked the hell out of them. And that's what you got, a T200-2. The T200-2 were some of the first iron core toroids that came out. The T means toroid, 200, 2 inches in diameter, -2, that was the iron powder. Let's mix some other stuff with this toroid. We'll call it manganese, zinc, copper, powdered stuff. Mix it all up, put the same glue in it, press it down, we'll call it ferrite. It's not necessarily, it doesn't ferrite, it's not ferrous, there's no magnet will stick to it. So we now have an FT number, which is ferrite toroid, a diameter in parentheses, which is the diameter in inches, and the mix number. And, there's all kinds of mixes that you can have. So FT240-43 is a toroid that's 2.4 inches in diameter, 43 mix. What did toroids do for us? The first they did is, first baluns were made for RFI, and then ununs were made for matching. Why did we use RFI and balance? Well, when you have a dipole and you feed it with coax, the outside of the braid is not isolated from the element that it's connected to. So that one element is the same length as the coax all the way to your antenna as it is to the where it connects to the wire in the air. So you had RFI or RF being radiated from the feed line. And so we used a one-to-one choke right there at the feed point, and that pretty much balanced things out. And it did the same thing for many beams, and it changed the patterns of beams too because it didn't off-balance them. It made them more equal. So, and then some of the first ununs were made for matching. Radios got smaller because of ununs. Some of the first really great examples of that were tank circuits and high power amplifiers. I noted that the 80 and 160 meter coils in a Titan, Tintec Titan, were made with stacked toroids that were wound with fiberglass tape. And the coil, instead of a matching coil that was yay long, now it was a toroid that was about that big around stacked. It was a sandwich like that in between two circuit boards with a bolt holding them down to the chassis. Pretty simple and worked great. Radios got smaller because coils were reduced. Tiny toroids were put in secondary windings for interstage transformers, and they were broad-banded, so they didn't need a lot of tuning other than squeezing the parts together, the turnings together and apart, and then putting some hot glue on them and call it a day. So interstage connection and isolation in a small package, rather than those big aluminum cans that you had to use a non-inductive screwdriver with to kind of tune them up. Now, putting a toroid at a right angle isolates the field from the two toroids and pretty much is really great for building small transistorized products. Who brought all this to ham radio? That was 1964 in Bell Labs. A guy named Turin, he pioneered the ferrite rod, which was a one-to-one balun, and the W2AU, or is it K2AW? Anyway, they're just basically a toroid rod with turns on it that turned into a one-to-one balun. You can see all kinds of schematics for these. Jerry Sevick in the 90s, he took off with this. He's now deceased. But he published a whole plethora of things in CQ magazine about one-to-one and four-to-one ratio baluns and ununs using toroid cores. Well, this took off, and then we found out that there were a lot of problems that we could match. New antennas came out, G5RV using a toroid to match ladder line down to coax, and then use that as a tuner situation. A lot of this work is published in CQ, and we're off and running. Later, he published a book with a lot of these, even more information than that in his thing about how to build different kinds of toroids. And this is his book. It's still in publication today, and for the most part, it's all pretty very accurate. But back then, they didn't have as many mixes as they have now. We have 52, 75, 61, 43, 31, and different mixes for toroids. But it's a good place to learn and a good place to read, and it explains all about toroid building and what the theory behind winding a toroid transformer is about. So with these toroids and antennas, we have one-to-one baluns, we have four-to-one baluns, we have 32 to 50 ohm matching transformers, and that would be used in a vertical for a matching of a vertical. We have 50 to 75 ohm matching transformer that you could use in a flat top dipole. And we have 50 to 25 ohm matching transformer, which is now known as a 49-to-1 transformer, and it's extensively used in the construction of in-fed half-wave antennas. So we go back to our original one matching section here, what we talked about. This is equivalent of a quarter wave matching section. What if we make it broad-banded? Well, how do you do that? Well, use a transformer, 49-to-1 transformer that has a wide frequency response, or a 64-to-1 transformer with a wide frequency response. This took the place of a loop-linked parallel tune matching and offered a very wide band coverage. So this whole situation here was substituted by a toroid, and it matched up very well, and you never had to go outside and readjust your match or anything like this. But what we really want to talk about is resonant antennas, which we have half wave, we have quarter wave, we have full wave, we have multiple wave antennas. But why resonant antennas? Well, resonant antenna is probably the most efficient transfer of power to be radiated and not used to heat up the system. A non-resonant in-fed half-wave antenna, or non-resonant in-fed antenna, not in-fed half-wave, but non-resonant in-fed antenna. They have a very high impedance. They require a step-down transformer, and that's usually a 9-to-1 unun, and it needs a wideband tuner. And the tuner will match that, and it will give you pretty much coverage on any band that you want. In-fed half-wave antennas, what are they? The advantage and disadvantages, buy or build, big compromise, and how well do they work? Well, an in-fed half-wave basically is a resonant antenna. There's a couple of types of them. One of them is inductively loaded to shorten it, and the other one is a full size. The frequencies can be anything that you design it for. The cost is marginal. You can construct them or you can buy them, and there's advantages to each in constructing versus buying, and in whether you buy it or construct it. The advantages, you can design the frequency that you want and the size or heaviness or however you want to do it, whether you want to put them in a backpack or you want to put them up for bomb-proof for everyday usage. The types of in-fed half waves. I mentioned a full length versus shortened inductively loaded. There's a lot of advantages to the shortened or the loaded version. They can be used for stealthy communicators and for INCOM things. You can throw them up in a tree and just get on the air really quick. Random length versus half wave multiple frequency. The random length requires you to have a wideband tuner to go with it, and it does not require any test equipment to set it up. You just cut it, put it to your tuner, hook it to your radio, and go. The half wave multiple frequency will require some other tuning equipment. And there's a single band in-fed half wave with parallel feed or a toroid. The parallel feed is a quarter wave matching transformer or a parallel matching network, which is basically a coil and a cap. The people that made the coil and cap were high in-fed antennas out of the Netherlands. They pioneered that for some time, about 10, 15 years ago. We have multi-band random length versus in-fed half-wave multi-band antennas. A random length in-fed antenna are not resonant on any frequency. And again, they require a 4-to-1 or 9-to-1 on and a tuner. And a tuner that is really wide-banded. In other words, 800 to 1,000 ohms of tuning capability. And that worst-case scenario means a 20-to-1 SWR tuning capability. A resonant in-fed half wave uses a 49-to-1 or a 64-to-1 unund, and a wideband tuner is not generally necessary because the SWR is considerably lower, generally 2-to-1 or less. Random linked in-fedders are not much different than a 43-foot vertical. Those are really popular for quite some period of time. People still use them. They still work pretty good. As long as the wire is not resonant on any band and presents a high reactance on all frequencies, a 9-to-1 unund will transfer the match to what is capable of the wideband transmatch. So your transmatch is capable of matching 1,000 ohms. Well, a 9-to-1 unund will make that transmatch capable of matching 9,000 ohms. So 9,000 ohms is pretty heavy reactance to load into a 50 ohm 50 ohm final on a transistorized radio. The problem with all this matching stuff is efficiency and loss. Do they work? Sure they do, but some patterns are not very usable. On a 43-foot in-fed, the pattern is almost 6 degrees straight up in the air on 20 meters. Not really all that desirable. Will it work? Yes, they work pretty good. If it's the only thing you can put up, then the best antenna you got is the one that's in the air. There are a few magic lengths for random length antennas. 58 feet, 75 feet, and 43 feet seem to be the ones that are most often used. These frequencies are not resonant on any band. The advantage is no analyzer is needed to build the antenna. You just cut it, hook it up to the 9-to-1 unund, and put your tuner on it with coax, and you're done. It may function, but will it work with your negative explicative of your very choice you can put here? And I say that because if you have 200, there are a lot of the 43-foot verticals advertise that they work really good as long as you have 150 feet of coax connected to the antenna. And therein lies, if you have a high SWR, then the coax is going to absorb some of that, and there's going to be loss in the coax. And then finally, by the time it gets to your antenna, you may have a 20-to-1 SWR that your tuner is going to match, and a lot of your power will be eaten up in your coax. So you better have good coax. It's all relative to your experience and radio compromise, radio and counterpoise system. This is a very unbalanced system and requires, in addition to a 9-to-1 unknown, it requires a 1-to-1 choke balance to keep RF out of the jack. Because the outside of the coax, the shield, is used as part of the other half of the balancing section of this antenna, your coax is actually radiating. So you can put a 1-to-1 choke balance right at the feed point of the 9-to-1 unknown, and then you can put a radial system at that point, and that keeps the RF off to the coax, and it actually has a better chance of radiating more efficiently. Without a radial system, it uses the coax as a radiator also. A resonant end-fed half wave requires more building. It requires an analyzer or SWR meter to adjust on one band, and then it will work with harmonic multiples, those being 80, 40, 20, and so forth, all the way up to 10 meters. It's harder to build and it takes more time to adjust. It can be set up in different formats that really work quite well. And personally have tried them as an inverted L, flat top, sloper, and V. And a half square may be constructed with this antenna with good radiation, easily obtained for gain or an omnidirectional pattern, depending on how you want to put them up. Resonant end-fed half-wave parts. Well, they take more time to build. You usually build them with a FT 240-43 toroid, mix 43. The wire is usually 12 or 14 gauge THHN stranded for the antenna itself, and I usually use 12 or 14 gauge wire, solid magnet wire, to wind the transformer. And an auto transformer, which is a wideband transformer, is what we're talking about. You have insulators and a box to put the stuff in. You buy or build. Well, you can build one, or you can buy one, or you can get one as a kit, and you can build half of it. And we're looking at here on eBay, and here's one, end-fed half-wave antenna, 1 kW. Well, I don't believe it's 1 kW. I mean, it may be 1 kW on sideband for not very long, but I'm not an advocate of running 1 kW on these end-fed half-waves because of the heat generated from hysteresis losses in the toroids. I think they're a great choice for somebody running under 500 watts, namely 100 to 200 watts. They work really good. This one's $38, and you don't have to buy the toroids. He's got two mirror. He's got good insulated wire. He's done a really good job of putting together, and he gives you a really high voltage capacitor to finish off your project with. Excellent choice. There's all kinds of this stuff out there, but I personally have used this guy, and they're really he really makes a good product. Let's go back here, and I want to get rid of this. How can I get rid of this? Here we go. Okay, so you can buy there, or you can buy this one, which I've used also very many times. I have it out in the garage, and this is a great antenna, matching coil. He does a really great job on all of his things. I'm not necessarily, I'm just saying what I've used and what I've had good experience with, and they work. And they're pretty darn bomb proof. And I've run this one with 800 watts into it on CW. And sideband for sure, 800 watts, no problem. CW, don't want to run too fast to CW with it. Generally, about 500 watts is all I recommend for even two stacked toroids because of the heat loss in the toroid. So anyway, let's minimize that. And we'll go to the next screen. And this, or you can homebrew one yourself. And this is one that I made, and I've used quite a bit. In the middle here, right in this middle, I usually fill that up. This one's quite done yet. I usually fill that up with hot glue. In other words, a whole big long stick of hot glue, and that fixes the things and makes it pretty bomb proof. No shaky or anything like that, because these things I just throw them in the truck. They're made to put up quickly and just get on the air, and when you're done, wind them up, throw them in the back of the truck, and go on. I use them with about 200 watts. That's about all I ever do. And it works very, very good. And that's just how I build them. If you look really close here, you may see some burn marks from lousy soldering. Well, you know, you have a few beers in the garage, your soldering iron gets a little close to the thing, that's right there. Other antennas. Well, an end-fed half-wave, let's see, that's 16, 33, 16, that's 65 feet. Well, that's 40-meter end-fed half-wave. But if you set it up so it's 16 feet, then go over 32 feet, now you have what's called a half square. We usually use a parallel tuner for this, at field day, my son and I put these up on some posts. We just use a post in the 5-gallon bucket, 2 by 4 in a 5-gallon bucket, and U-bolted posts that go up 16.5 feet, and then run a wire between the two posts, and that's what our 20-meter antenna is. It gives a really nice bow tie pattern, and it gives you about 3 point some dB gain, and it's very low angle radiation. So we used a field day and did great. 800 contacts later, we think that's a win. Okay, just on 20 meters. We don't use it on 40. We just use it on 20, and that's about the only thing we use. Infed half-wave building, you can make a shortened length. And the reason we use a shortened length is because a lot of people don't have 130 feet for 80 meters versus 70 feet for a shortened length. The efficiency is best on 40 through 10 because it's a full-length half-wave antenna on 40 through 10. I mean, there is compromised performance on 80 because it's not a full 130 feet on 80. It's shortened 70 feet. How do we do this? We inductively load it. In my opinion, it's the best of both worlds. It's shorter and it's resonant. It operates on most bands with reasonable efficiency. Because 85% of almost all contacts are made on 40 and 20 meters, and because it's shorter, it has a better chance of staying up. In other words, less wind resistance and stronger wire, less spans, less ice loading, less ice on the wire. It stays up better. It's great for NVIS and DX, depending on how you put it up, and it's great for an FT8 all-around antenna. 80 through 10, one and done, less than 2 to 1 SWR, and it's great. How does it work? Half-wave dipoles, 50 ohms in inverted V at the center. Well, somewhere between 50 and 70 ohms, depending on how high above the ground and other varies. Moving the feed point of the antenna from the center of a half-wave dipole to 1/3 out makes it an off-center fed dipole, which is a very unbalanced antenna, but you need a 4 to 1 balance, to match the 200 ohm load down to 50 ohms. If you get any metal close to this antenna, it's really sensitive to that, and your SWR kind of goes crazy, and you'll never get a match. And it talks to almost every antenna that you have in your backyard. So I'm not necessarily they do work, they work reasonably well, but you have to be careful where you put it, off-center fed dipoles. But if you continue to move that feed point out to the very end, the impedance is about 2,500 ohms or so, depending on the installation where you're at. Coax is 50 ohms, infed half-wave is 2,500 ohms. A 49 to 1 UNUN is almost a 50 to 1 transformer. So if we have 25 ohms divided by 50 ohms transformed to 50 ohms. So a 50 to 1 transformer, 50 into 2,500 gives 50 ohms. It works pretty good. That's not all. Once the transformation is done at the primary frequency, it also transforms the mismatch as one varies the frequency of the radio. In other words, up and down the band. It matches it perfectly. This decreases the mismatch with varying frequency by 50 times. How does this work? What's SWR? Let's look back at it. Well, SWR can be defined in many ways: forward current, forward power, forward voltage versus reflected current, reflected power, reflected voltage, respectively. If you have a 20 to 1 SWR, which is pretty darn bad, it means that you have 1,000 ohms of reactance coming back at you. So, 50 times 20, 1,000. So if the reactance is 1,000 ohms and the SWR is 1,000 divided by 50, which is 50 ohm feed, gives you 20 to 1. The tuner will handle it, but generally at a much greater power reduction. Canceling the reactance with the tuner is heating your shack and becoming a really nice ozone generator, and the internal components are not rated high enough to handle, if they're not rated high enough to handle the power and the voltage that you're applying to the circuit. This isn't good. I want to radiate RF, not heat. You can't talk with heat unless you're in a political debate. There you go. Tuners, here's a laugh. I'm not an advocate of tuners, as you can well see. For years, alpha amplifiers have been the gold standard of amps. Now they're making a tuner. Guess what's inside a tuner? Anyone have any idea? Let's take a look. Here's their latest and greatest tuner. Let's look down here. Circuit design. Oh, it looks pretty good. Oh, it looks vacuum transformers. Looks pretty good. Cooling. Who in the hell ever heard about cooling inside a tuner? Oh, at this power level, it generates heat. Therefore, we put 2 muffin fans in to keep this thing from melting down. You can read it. They said it right here. There it is. Anyway, so that's what they're doing now. SWR, worst case 20 to 1. What does it mean? 20 times 200,000 ohms. In-fed half wave, 1,000 additional ohms for bad matching wire. Then the total is 3,500 ohms. So you have 2,500 ohms at the feed point, plus another 1,000 ohms of reactance. So you have 3,500 ohms. Your unknown is approximately, your transformer is approximately a 50 to 1. So 50 into 3,500 is 70 ohms. 70 over 50 is an SWR 1.4 to 1, and that's why these work. If you have a bad match, it transforms a bad match because of the magnitude of the auto transformer. Because this transformer, it will work with less efficiency on the work bands, but yes, it will work. So you may get a 3 or a 4 to 1 match with no tuner, but just straight match, straight across. And generally, it's a straight 3 to 1 clear across the band. And this is because the work bands are not direct harmonic multipliers of the primary. The efficiency is much lower. And if you do run the work bands, because your higher SWR is going to create more heat and the transformer don't run as much power. Shorten in-fed half wave with an inductor. This is my all-time favorite antenna for getting new guys on the air so they can learn the bands and at least have something to operate on every band that doesn't cost them an arm and a leg to build. Basically, this is a half wave on 40 meters, and you tune that half wave to exactly 7.1 megahertz. Then adding a pigtail after the inductor at the end of the 7.1, at the end of the 66 feet, you put the inductor, then add 6 feet of wire, and this will resonate about 60 kilohertz under 2 to 1 anywhere in the 80 or 75 megahertz band. For most people, you don't generally vary on 80 very much. A lot of guys just sit there on their phone band and they talk about the weather every night. And they're good with about 60 kilohertz on 80. If you're running CW nets on 40, I'm on 80, well, that generally covers 60 kilohertz, so it works fine. Doing this decreases the bandwidth of the antenna on 80, but allows a shortened antenna on 80 to still work well. In other words, it fits in your lot. Instead of 130 feet, now it's only 70 feet. Here's what it looks like. There's your 110 microhenry coil. This is an in-fed half wave again, and this is how I make them. You notice the blue capacitor at the bottom that kind of tunes out some reactance and makes the link coupling match up better for 10 and 15 to a marginal amount 20. Doesn't do much for 40 or 80. At field day, toroids do heat up with power, and this is a new thing. We were shutting down field day. I forgot to bring an 80-meter dipole with me, so I had this thing in the truck. I says, well, this will work on 80 for CW. So we were shutting down. Another guy wanted to use phone on one of the antennas, and my son and I wanted to use CW, and I was on 80 and he was on 40. So what we did is we took a diplexer, an 80-40 diplexer, and we took 2 bandpass filters, one on 80, one on 40, and we connected my transmitter to the 80 and his to the 40, and we ran both of the transmitters directly into the bandpass filters into the diplexer out to this match up here, and we were both running 100 watts continuously at 30 to 35 words a minute CW, and after about an hour and a half, our SWR started to climb, and we noticed that it got kind of hot. Now, as I told you earlier, I fill the center of these toroids with hot glue to kind of keep everything glued down so it doesn't bang around in transport. Well, this little bit of jizzle right down here, it got so hot that it melted out the hot glue out of the center. This whole thing was covered in the center up to the top, and it melted it here. So these things can get really hot, and that is an efficiency situation, but we still managed to make about 500-600 contacts on field day using this one antenna, using 80 and 40 on this antenna. It was just fine, no problems. And we both used it at the same time. I think probably made more than that on it, but there we went. This is how I make that coil. The coil is just PVC. It's got about 60 turns of 18 gauge wire on it, and coat it with a liquid electrical tape. And while it's still liquid and sticky and runny, you put Scotch number 33 or Scotch 88 over the top of it. And that kind of vulcanizes it, makes this thing bomb proof. Really, really, you can drag it across this concrete and won't even worry about anything. Works great. So, this is a perfectly excellent product made by Ballon Designs. And I love them. That's where I get it. And I've used this one. And do they work? Well, yeah, they work. Using that one that you saw there, I used a 33-foot wire on a spider beam pole, and a spider beam pole is 40 feet fiberglass fishing pole, basically. Use it as end-fed half wave on 20 meters using the 49-to-1 unon, so 33 feet, so half wave on 20, and then a quarter wave on 40, and 3 half waves on 15. Yeah, what I did is I put a bypass so that I had to go out and change the wire from the in-fed half wave 20 to over to a pass feed through so I could run it on 40 and 15. But that wasn't any big deal. I spent 8 hours with a car battery in 38-degree weather in a barn sleeping on hay. The battery went dead, but oh, what fun. And this is what happens. Number one in United States first call area, QRP, WPX. So yes, they work very fine. They work great. And that was my only antenna that I used. Commercial, you can buy them. What does the inductor do? Well, the inductor shortens the antenna. By adding an inductor, it does two things. At the blocking frequency needed, you need about 3,000 to 4,000 ohms of reactance to work the inductor, so the inductor functions as a choke. Lower than that frequency passes the RF and allows it to function on a lower band. In our case, it passes 80 and 75, but chokes 40 and above by being a choke, because at 40, it presents 3,000 to 4,000 ohms of reactance, so it functions as a trap. How much inductance is needed? How to figure that out? Well, a lot of times when you read about in-fed half waves, they give you this magical number of 100 to 110 microhenries. Well, I went to Ballon Designs because I don't have any of this test equipment, and they publish what it takes to stop RF on the outside of a coax shield. And I went, well, that's to stop RF at any frequency. You need X amount of ohms at this frequency. So I figured it's between 3,000 and 4,000 ohms, and that's what they sell their ballons that produce. So I said, okay, I need to stop 3,000 or 4,000 ohms on 40 meters. So I go to this little calculator here, and it's right online. And I picked it up, and they just enter in, okay, capacity reactance. No, we want inductive reactance. We want to enter microhenries. We want microhenries, and we want to enter inductance. We want to enter frequency, and we'll say 7.1 for 7.1 megahertz, and we want to enter inductance. We put in 100, and we get 4,500, basically. If you want to go 110, you get 5,000, and that's what a lot of people use. 5,000 ohms of reactance works really well, and what it essentially does when you're using 110 microhenry blocking a 40-meter signal, you get absolutely no interaction between the pigtail and the primary piece of wire coming before the inductor. I mean, it's like a switch. It's an open switch. When you get less, let's just say 90, which I've used 90, and you get 4,000 ohms. So what is this telling you? It tells you that you really don't have to be a brainchild to wind a coil and all anxiety about it, because anything between about 58 and 70 turns of wire is going to be perfect for this coil on an 1.5 inch diameter form. And so you're good to go. And that's 1.25 inch PVC, about 60 turns. Anything between 58 and 65 turns is fine. It'll work just fine. It works great. Just cut it and forget about it. All right, minimize that. And so there you have it, between 90 and 100. I use a 90 a lot. It's a little harder to tune because it doesn't necessarily block all the signal. It doesn't choke off all the signal. So there is some interaction between the primary 66-foot length and the pigtail. There is some interaction, so it takes a little closer time to cut those pieces to make it resonant at 7.1 megahertz, and then again to make it resonant at the 80-meter frequency that you want to have. Does it really matter so much about the resistive losses? No, not too much, because there's no real heat loss in that coil. We've run 1500 watts into coils on dipoles made exactly the same way, and they never get hot and change frequency or do anything. So I say not so much. How does it radiate? Well, that's always a question everyone wants to ask. Well, how does my dipole work? How does it work at this height? How does it work at that height? I'm not necessarily a smart man, but I know where I can find information. And this right here, folks, is like the best thing. You notice this is all about wires and wire dipoles and anything you ever wanted to discuss about an off-center fed or an in-fed. Now let's look at a sloping, which is one of my favorites, and then it starts going through all the different patterns of the sloping dipole at all the frequencies, and you can see what there looks like and what your pattern looks like. Actually, if you're sitting in the backyard, that doesn't look too darn bad. I mean, it's omnidirectional, and if you put the wire east and west, guess what? You're covering East Coast and West Coast in your center of the United States. Not too bad. I'll take it. Particularly for the new ham that doesn't know anything about it. It's a pretty good antenna. It lets you get on. And you can read about any kind of antenna you want on that page. And it gives you really good information about feeding a dipole, the height for feeding, the positioning of the different antenna, whether it's a sloper, vertical, sloping, and inverted L. It covers them all. It's really an excellent, excellent web page. And I use that when I have a question to answer for myself. Conclusions. What are the pros and cons of these? Well, the pros of this is easy to run coax and it only needs 2 supports. In other words, you're not going to be spending a lot of money on coax because one end is not halfway through the antenna. One end is right close to your house where the coax comes into your house. 10, 15, 20 feet, you're done. So it's cheaper, cuts down on coax. It's a multi-band antenna with reasonable efficiency. It fits almost anywhere. You can make it as an inverted L, a sloper, a flat top, even a half square if you wanted to. It's great for emergency usage and field day because you can wind it up pretty nice. And it's stealthy for an HOA. You make it black, it pretty much disappears and spray paint your coil black and everything's fine. Cons. Construction. It does take some time. It does take a meter to resonate it, an SWR meter to resonate it at 7.1 megahertz, and then again on your 80. But you can drop off the 80 coil and just have 40 through 10 with no problems. Costly to buy for what you get. If you were to buy this thing, they're upwards of $200 on the eBay and all kinds of other. The people are advertising the heck out of these my in-fed antennas. There's just a slew of them on eBay and Amazon that are selling these things. But what they are is a 49 to 1 on and a piece of wire and a plastic box to put them in. How hard is that? Most of us could probably do that. It's probably pretty hard to find a shortened version, but you can. InFed's antenna, high InFed's antennas out of the Netherlands makes a shortened version from 80 through 10. I would have to say it's probably one of the best ones on the market. Commercial versions are overrated and underbuilt. They always tell you that they run more power than they can, but I tell you, I don't believe that because of the heat loss. I want something a little more efficient. RA6LBS is low band systems. He manufactures multiplexers and diplexers in Russia and shipped here to the United States and distributed by DX Engineering. On his webpage, he makes a 1.5 kW InFed transformer. It looks pretty darn beefy. I might trust that I would run 1,000 watts in it, but there and again, this to me is a solution for a low power station. I don't advocate using it with high power because high power means higher losses and higher amperage and higher heat, and it changes toroids, and it's just too much. I think you can get away with tons of stuff in the QRP world that you would never even think about with a 100-watt station or a 500 or 1,000-watt station. Oh my God, you can do crazy, terrible things with, your feedback's 500 milliwatts. When you're running 1,500 watts into it, it's 150 watts. Oh my God, you're just burning up yourself. It's like grabbing a hold of a soldering iron and some of this stuff. So anyway, if you have any questions, you can always call me. I love to talk antennas, contesting, and station building. And here is who I am. And thank you for your time. Any questions?
Okay, thank you, Morgan. Okay, does anybody have any questions for Morgan? And remember, you are muted. And any questions, we're going to keep very short right now. And Morgan, what we usually do is open up.
I'll be back if you want to continue on with your meeting.
Yeah, we'll open up a breakout room after the meeting.
Sure, I'll be
And
around.
you're welcome to stay for the business meeting and to also to answer some questions right now. So if anybody has a couple of brief questions for Morgan, go ahead.
This is Peter W0NG. I'm going to ask you a question in the breakout room.
Okie doke.
Okay.
Yeah, this is Vic. I got a quick one. You haven't mentioned anything about 160 meters. Is that just because they're very long or is it because they don't work?
They will work just fine, but your primary frequency is going to be on 80. Okay. And have you run any power on 160?
Just 100 watts.
Okay. Well, 100 watts isn't critical. When you start running 1,000 watts on 160, I set my backyard on fire with arcs off a loading coil sitting on a breadboard transformer in the backyard. So 160 is a crazy band. There's a lot of crazy stuff. If you run 160, you have to be careful. Because the voltages are really high, on the end of your pigtail on the 160, you should put a ring connector because you'll have a nice corona and eventually it'll start eating it off. No, seriously, the voltage is really, really, really high. So be really careful on 160. It's nuts. 160 is a very difficult band to operate. You would run 133 feet and you resonate that on approximately 3.6 megahertz on 133 feet. Then you would put 174 microhenry coil to stop the 80 meters, and you'd run another 15 feet or about 17 feet of wire, and that gives you 160. So you'd have 160, 80, 40, 20, 15, and 10 all on one antenna at one feed point. But you would have to have roughly 140 feet of wire space. You could set that up as an inverted L, a sloper, or as an inverted V.
I have the space. I'll contact you. Thank you.
Sure. I use that 174 microhenry coil in my installation here, but I use it as an inverted L on 80, and at the end of the L I put 174 microhenry, and then I put about 15, 20 feet after that, and I get 160 out of it. And that's what I use. My entire 160 through 2 meter antenna system fits in 68 linear feet.
That's incredible. Thank you.